Let's talk about the hidden chemistry that's all around us. I mean, it's in the drink in your hand, the radiator in your car. There's this invisible science happening in pretty much every liquid you can think of, and that's what we're going to dive into.
You know that sound, right? That psst when you crack open a can of soda? So satisfying. But have you ever stopped to think about what's really going on in that moment? What's actually making all that fizz? Well, that's exactly where we're going to start.
So, let's get right to it. The science behind that soda fizz. Because it turns out, that simple sound, it's like a secret handshake that lets us into a really fundamental concept in chemistry.
Okay, so the simple answer? It's all about pressure. I mean, a ton of it. Think about it like this. Imagine you're trying to shove a bunch of extra people into a room that's already packed. That's basically what soda companies are doing. They take carbon dioxide gas and use massive pressure to force it, to cram it into the liquid.
And this isn't just some random trick. There's a rule for this. It's a scientific principle called Henry's Law. And what it says is actually super simple. The more pressure you put on a gas that's sitting on top of a liquid, the more of that gas is going to dissolve into the liquid. It's a perfect one-to-one relationship.
And this is the math that proves it. It looks simple, and it is. C here is just how much gas is dissolved, and P is the pressure. So you push up the pressure, P, and the amount of gas, C, goes right up with it. That's why when you pop the top of the can, psst, the pressure is released, P drops like a rock, and all that extra carbon dioxide that can't stay dissolved anymore comes rushing out as fizz. Okay, so that explains how much gas we can cram into a soda. But that leads to a much bigger question, doesn't it? Why do some things mix in the first place, like carbon dioxide and water, while other things, like the classic oil and water, just refuse to? It all comes down to the molecules and how they feel about each other.
So to get this, we got to understand that there are two kinds of forces we're dealing with. First, you've got the intramolecular forces. Think intra like internal. These are the super strong bonds inside a single molecule, like the glue holding a water molecule together. But then you have the intermolecular forces. Inter means between. These are the weaker attractions between separate molecules. These are kind of like the social rules of the molecular world. Who hangs out with whom?
And this diagram just shows it perfectly. See those solid blue lines? That's the strong stuff, the intramolecular bonds holding the atoms together inside one molecule. But then, look at those dotted red lines. Those are the intermolecular forces. They're the little attractions that make one water molecule want to hang out near another one. It's why water sticks to itself. And all of this leads to probably the most important rule in all of solutions chemistry. It's a simple little phrase, like dissolves like. So simple, but it explains so much. It just means that things with similar personalities, similar intermolecular forces, are going to mix together just fine.
Yeah, think of it like a high school cafeteria. You've got all these different cliques, right? Well, molecules are the same. They have different types of intermolecular forces, which are like their social groups. You've got the super strong hydrogen bonding crew, and then you've got other weaker groups. Water is part of that popular, strong hydrogen bonding clique. Oil, not so much. It has much weaker forces. So they just don't mix. They've got nothing in common to talk about, molecularly speaking. All right, so now we know why stuff dissolves. But what happens next? What happens to the liquid after something has dissolved in it? Well, it turns out that just having those dissolved particles floating around, we call them solutes, can totally change the game for the original liquid. This is where we get into something called colligative properties. And the key thing to remember here is that for these properties, it doesn't matter what you dissolve. Could be salts, could be sugar, whatever. The only thing that matters is how much of it you dissolve. It's purely a numbers game, quantity over quality every time. And the best way I've ever heard this explained is to think of those solute particles as party crashers, right? You've got the original liquid molecules. They're having a nice, orderly party. They're trying to do their thing, whether it's boiling or freezing. But then, in come the solutes. These party crashers are just getting in the way, bumping into everyone, causing chaos, and making it way harder for the original molecules to do what they were trying to do. So let's take boiling, for example. To boil, a water molecule needs to get to the surface and jump out into the air. But now, the surface is crowded with all these party crashers. They're blocking the exits. So for a water molecule to escape, it needs a lot more energy to push its way through the crowd. That means you have to get the water hotter than normal to make it boil. And we call that boiling point elevation. And the exact same idea works for freezing, just in reverse.
To freeze, water molecules need to link up in a very specific, neat crystal pattern. But, you guessed it, the party crashers are in the way, breaking up the formation. They can't get organized. So you have to make it even colder than normal to slow them down enough to force them into that crystal structure. That's freezing point depression.
Okay, let's bring this all home, because this isn't just stuff that happens in a chemistry lab. This is chemistry that's happening in your daily life, probably without you even realizing it.
Ever wonder why we throw salt on icy roads? That's freezing point depression in action. The salt particles get in the way and stop the water from freezing. What about the antifreeze in your car? That's a double whammy. It uses these principles to stop your engine from boiling over in the summer and from freezing solid in the winter. And yeah, even when you salt your pasta water, you're raising the boiling point just a tiny bit, which makes it cook at a slightly higher temperature. So you see, from the soda you're drinking to the roads you drive on, these principles of solutions are everywhere. It's like this hidden layer of science, constantly working behind the scenes, shaping the world around us.
And it kind of makes you look at things differently, right? So here's a thought to leave you with. What other hidden chemistry is at play in your world, right now? What other everyday magic is just waiting for an explanation?